Hello everyone, my name is Ramin. I am project management intern with the Vector, and today I want to talk about the collaborative project that I was involved in, which was identifying and mitigating climate change challenges using computer vision. All right, okay. So as I present this project, I'd like to take a moment to clarify my role within this dynamic team. As an applied AI project management intern, my primary contribution was in facilitating the flow of information and resources among team members. My responsibility was to ensure that our collaborative environment was well coordinated, which allowed the brilliant minds in our team to focus on innovative and problem solving. This project is a culmination of an extraordinary collective effort. It was made possible through the dedication and expertise of over 28 talented individuals across 6 companies. Together, we brought a diverse set of skills and perspective that were crucial in driving this project toward impactful results. I'm proud to have supported the infrastructure of our collaboration and enabling the teams to excel in their respective roles. So let's have an overview of the project. Each row here signifies a unique project demonstrating the versatile application of AI in climate change. First, we have the PwC's work leveraging computer vision to understand land conversion, a project that uses computer vision to monitor changes in land use, providing insight into how land conversion impacts our environment. Then moving on, we have charting the Congo corridor by RiskThinking AI, which is an initiative that maps one of the most vital ecological corridors in Africa using computer vision to analyze satellite imagery and help in conservation and sustainable management efforts. And then we have Scotia Bank that has taken a proactive approach with wildfire detection with computer vision. This work is working on leveraging computer vision to detect potential wildfires, potentially saving lives, resources, and preserving natural resources. Then Telus has focused on AI for environmental monitoring, employing computer vision to observe and report on various environmental indicators, ensuring timely interventions for ecological preservation. And finally, the co-development team has been working on a foundation model for climate change related downstream tasks. This foundational model serves as a versatile tool for various climate change mitigation strategies, helping to streamline and accelerate our responses to environmental challenges. This slide highlights the distinct feature about our project. So firstly, the collaborative spirit of this project is unparalleled. We have pioneered the co-development of solution by members from diverse sponsor organization, including BMO, RiskThinkingAI, Skywatch, Telus, Scotia, and Vector Institute team. The second point is our commitment to knowledge sharing. We are aiming to open source 4 to 5 innovative solutions that address climate change challenges. This solution stem from the collaborative work of the mentioned sponsors, in addition to the co-development team. And then from the project management point of view, we utilize agile methodology for project management and solution creation, which enabled us to work efficiently with stakeholders and a significant number of participants that we had. This ensured that we remain responsive to the evolving need of the project and also maintaining the flexibility. So let's start with the industry-driven project. I'll start with the PwC, which was leveraging computer vision for understanding land conversion. The context for this project is driven by the upcoming disclosure requirements such as TNFD, CSRD, and SBTN, like we can talk about them later, and underscoring the necessity for companies to gain a deeper understanding of how their operations impact ecosystem services, particularly through land use and conversion. This understanding is crucial as it directly relates to the sustainability and ecological footprint of an organization. However, we face a significant problem, which is available data is rarely standardized, especially on the global scale. Different jurisdictions have varied requirements for the data collection and interpretation. Moreover, the existing data sources often lack the granularity needed for the model. By harnessing the power of satellite imagery combined with the computer vision, the project aimed to accurately track changes in the land use over time within a specific regional boundaries. And on this slide, we dive to the mechanics of how the PwCs has approached the challenge of monitoring land conversion. The team started with 4D, one high resolution RGB images. Then the images the resolution for each of these images was 25 to 50 centimeters per pixel. They manage this data and convert them to the 256 to 256 pixel batches, and then train the unit model that they have to see whether they could have any pixel-wise prediction of the type of the land use that they were looking at. And the type of the land use that they were interested in was building, land, road, and forest and water bodies. And what they realized was that based on the data that they have and the model that they used, they were able to reach the accuracy of 92% pixel wise, which shows the feasibility of tracking using the satellite images to track the type of the land use that we have. Then, turning our attention to the next slide, we focus on Risk Thinking AI's project, which was charting the Congo corridor. This project is set against the backdrop of major global crisis, which is deforestation. We've lost one third of our of the world's forests, a staggering statistic that underscores the urgency of our work. The Congo Basin, often hailed as the Earth's second lung, exemplifies this crisis, having lost over 600,000 hectares of the primary forest in 2020 alone. If the current rate of deforestation continues, the alarming projection is that Congo Basin could vanish by the end of the century. So risk thinking AI confronts this problem with a solution that combines satellite imagery and computer vision. The solution is engineered to track changes in land use by focusing on a specific regional boundaries. The project aims to provide a detailed analysis of land conversion over time, which is vital for conservation efforts and policy making. So here we're also looking at the land use changes, but we with more focus on the local and the regional changes rather than let's say pixel-based things. And then, so what you can see here is that these are the regional jurisdictions that they want to look into and how the conservations are happening into these within these regional lands. And then they want to report what's happening and the changes in the land use in a time domain of yearly and monthly, and then help the regional bodies to decide about the measures that they want to do. So what we're gonna say is that post conservation, this baseline that they're gonna develop will serve as a measure against the future land use pattern, allowing us to evaluate the success of conservation program as like it could be seen in the photos. And then we have the Scotia Bank, which was tackling the wildfire detection using the computer vision. So they wanted to see whether there is a way to leverage the satellite images and computer vision to develop a tool that could provide a data-driven risk assessment strategy. A Scotia Bank solution to this challenge is a computer vision-based tool. Objective is to detect and map the regions affected by wildfires accurately. By doing so in a defined region and in near real time, the Scotia Bank can provide actionable intelligence to respond to these disasters more effectively. With this tool, Scotiabank is not only positioning itself at the forefront of technological innovation, but also demonstrate the commitment to safeguarding the natural resources. And to enhance the context of their work, they are focusing on confirming the accuracy of the fire detection by validating their method with more examples. This step is is essential for ensuring the reliability and trustworthiness of their detection system. They are also investigating the feasibility of scaling their detection capabilities to map wildfires across entire regions, such as provinces, without the need for external data on fire location. This would mark a significant leap in achieving the autonomous monitoring. As for feasibility and scalability, we are conducting tests with various data sources to refine the automated elements, further ensuring that our solutions are robust and scalable. And then we have the Telus that are exploring the AI for environmental monitoring. The event triggering this needs is clear. Ecosystems around the globe are undergoing unprecedented changes. These changes, driven by extreme weather events and the spread of invasive species, present significant risk not only to the environment but also to the socio-economic fabric of our communities. It's critical that we monitor these changes to understand and effectively address the resulting climate impacts. So Telos is developing a solution through its environmental solution team to advance ecosystem monitoring techniques and pioneering the use of ground-based and crowd-based imagery to enhance the accuracy of the accuracy and the breadth of environmental data collection. So here, instead of having the satellite imagery, we have the images that are taken from the ground level, and they are looking into monitoring the changes over time. And then we have the co-development team project. So as we looking at the slide, we delve into the co-development team innovative efforts to harness the segment anything model for environmental application. And we all know that the SAM could be used in areas like the forestation monitoring, agriculture, land use, ocean and water body analysis, and natural disaster response and beyond, offering new insight and capabilities in environmental stewardship. However, the application of SAM to these critical areas come with its own challenges. The limitation include the field of view, as SAM is trained on the natural objects that may have different perspective compared to the satellite imagery. The model's performance is also tied to the spatial resolution of the satellite images, which can be limiting factor in certain application. Additionally, spectral limitation and the challenges of scalability and the challenges of the scalability must be addressed to fully realize the potential of SAM in the context of climate changes. So this slide here takes us into the heart of the technological advancement here. Firstly, let's talk about the spatial resolution. Our team has successfully applied down sampling technique to incorporate aerial images with varying ground sample distance. So this allows the model to analyze images with different levels of details, from broad 3-meter GSD for a general overview to a detailed 0.3 meters GSD for fine grain analysis. And when it comes to the spectral limitation, the team is actively exploring ways to enhance SAM's capability. This includes adding new spectral band beyond the standard RGB, which could provide a wealth of additional information. And finally, addressing scalability, we have implemented two innovative methods for automatic mass generation, which is one of the common issues with our industry partners. The first is a custom decoder, which creatively replaces the standard mass decoder to generate a precise mass for objects of interest. The second method is prompt tuning, involves a trainable prompt embedding that can bypass the sparse prompt encoder, offering a more direct and efficient way to generate these masks. And then as I bring this presentation to close, I would like to extend a heartfelt thank you to the sponsors and everyone who played a role in the success of this project. Special thanks to the management team, interns, and the associate applied ML specialists. Thank you. Thanks, everyone.
Great job. Okay, any questions or comments from our judges?
Hi, Ramin. I just
Yeah.
have one question, right? The
Hmm.
first project that you presented where I think the segmentation using UNet, right?
Yes, yes.
Uh, so this obviously is a semantic segmentation problem.
Yeah.
I'm just curious why you are reporting pixel-wise accuracy rather than mean intersection over union.
I guess the main reason that they had for this the specific task was to compare it with the other literature in the field of satellite imagery. I'm not sure what was the exact reason, but that was how they decided to present their performance.
Okay.
Yeah, thank you.